completely different. Chapter 24, Pericyclic Reactions and the Diels-Alder. What's up with that? Well, it's wildly different from what we've been looking at so far. Pericyclic reactions fly in the face of what we've learned so far. After all, we've learned nucleophile and electrophile over and over and over again. It was only recently that we introduced a new player, that being our R dot, our radical, where the clue is either heat or light, and the absence of, the absence of polarity. Now, we've got that same kind of deal, no pun intended, get it, Diels-Alder? No, now we have the same sort of thing. We have some reacting pieces that don't make sense in terms of polarity. Diene and a dienophile? They react? Neither one is a particularly strong nucleophile, and sure doesn't look like we have an electrophile around. So why do they react? Is it magic? No, it's all orbitals. So a diene and a dienophile react in a very slick little mechanism, like so. To make a cyclohexene. Okay? So that's called the Diels-Alder reaction. There are other pericyclic reactions that we'll see in this chapter, but we're starting with this one because it's a powerhouse in terms of making new bonds. After all, as you can see, we just made 2 new carbon-carbon bonds. That's pretty special. Alright, how special is it? It's unbelievably special. It's super powerful. We are trying to make this pretty dang complex molecule down here, lepinine, and we are making it from this starting material, which of course that was made from, a multi-step synthesis to get this far, of course. But look at what the Diels-Alder does. The Diels-Alder takes this somewhat more simple starting material and ties together those bonds to make that product, all in one swell foop. Pretty impressive. So it's extremely powerful synthetically, but as you'll see later on in this mini lecture, it's also really important in terms of biochemistry as well. So what is the mechanism for the Diels-Alder when we don't have any nucleophiles and we don't have any electrophiles? Well, it's a single step, meaning there are no intermediates, and basically it just has this cyclic transition state. So you start by putting your electron movement arrow, your source of electrons, right on one set of pi electrons, and then push them all the way around. Basically it's 3 sets of electron movement arrows. And when you draw in those arrows, what you'll see is that you get a 6 pi electron aromatic transition state. So let's do it again here. Doot and doot and doot. So let's make it more obvious. This arrow is showing the formation of that bond. This arrow is showing the formation of the double bond that will end up being the cyclohexene, and this arrow is showing the formation of that bond. So it's a very low energy transition state because of its aromaticity, and again, as you can see, you end up with a cyclohexene in the product. Now, what else is attached is what you get from what's attached on your starting materials. So, as in this example, you can see we've got all of this spaghetti attached to the dienophile, and here it is in the product. And just, it's kind of obvious, but the dienophile is the alkene, that likes dienes. Get it? It's a dienophile. Organic chemistry nomenclature sometimes leads you to wonder. Okay, so there's no electrophile, there's no nucleophile, it's all orbitals, and that's why I bring section 24.10 up earlier in the reading. Because the whole reason this works is because these orbitals, the molecular orbitals of the diene right here and the dienophile right here are of the correct phase. So as you look at these two, here's my diene, you can see that the blue lobe on the diene is going to overlap with the blue lobe on the dienophile. And the red lobe on the diene will overlap. They're both in phase. It's constructive overlap. That's where my new bonds are coming from. All right, let's look at it in a little bit more gory detail. Here is what we learned in chapter 14, the molecular orbital diagram for a diene. This will be, we'll say this is butadiene. And basically there's 4 electrons in my pi system, so I have 4 p orbitals. Here are my 4 electrons. So we know these 4 molecular orbitals. We know that our dienophile, ethene, has just the 2 molecular orbitals and the 2 pi electrons. And so as we look at our HOMO and LUMO, our HOMO is right here. It's the highest occupied molecular orbital on our butadiene. And our LUMO is the unoccupied molecular orbital on our dienophile. And what the little dashed lines are signifying is that, just as you can see, these two are in phase so they can overlap, and these two are in phase so they can overlap. So if we look at that again in our previous slide, which will only take us 4 days to get to, that's exactly what this image is showing you. That we have in-phase overlap here, in-phase overlap here. We're just curving the electron, the diene around so that you can see how they overlap. All right, now this Diels-Alder reaction, where the dienophile and the diene can overlap because the LUMO and the HOMO have the right phase, that's called symmetry allowed, and that's why the reaction works so well. So, heck, why don't we just show, alkenes doing this? I can certainly draw pretty little electron movement arrows that show the same kind of thing. Let's have an ethylene react with an ethylene to make a cyclobutane. Why not? Well, because of the orbitals. That's why. If we look at the orbital energy diagrams again for our 2 reacting partners, our ene and our enophile, I guess that's what you'd call them, well, we're going to have to take the HOMO of one of the 2, and that's going to have to try and react with the LUMO of the other one. And you know what? That's not going to work. Okay, so while I can get one lobe to match up in the pi system, the other lobe is destructive interference. They're of opposite phase, they'll destroy each other, and there won't be a bond formed. So this is an example of a symmetry forbidden reaction. It doesn't happen. It doesn't happen because the HOMO and the LUMO don't match up. However, there's always a however, right? However, what if our whole HOMO and LUMO thing changes around? So again, we've got our 2, our ene and our enophile, and the HOMO of the one is still the same, of course. But what if we zap the molecule with H nu, or energy from heat or whatever, to promote one electron from the ground state up into the excited state. Well, no problem there. We see that in UV vis all the time, right? So that happens. We know that happens. And what has that done for us? Well, then suddenly, what that does for us is it sets us up with a new set of HOMO and LUMO. So now my highest occupied molecular orbital is the singly occupied pi star orbital from one of those alkenes, and the LUMO is the empty pi star orbital from the other alkene. And what can you see? Well, what you can see is they're clearly going to be able to line up. So when that happens, you can get a reaction to take place, and the two alkenes dimerize, and you make a cyclobutane. And that is, in fact, exactly what happens in biochemistry. And it's not a good thing. So when you look at thymine bases in our DNA, well, what do we have here? We have two alkenes. And, of course, they're sitting right next to each other, because after all, this is DNA, and everything's tied together. So if I hit my DNA with light of the right wavelength, dad blame it, then I can get this kind of reaction to take place. So a 2 plus 2 cycloaddition, where 2 plus 2 is referring to the 2 pi electrons plus 2 pi electrons in the 2 pi systems, then we get a nice cyclobutane, as indicated by this drawing, and this is out of your textbook, of course. And then, the bad news here is that totally mucks up your DNA. It can't unzip and zip back up again, and basically this leads to skin cancer. But what it is illustrating here, the good side of what it's illustrating, is the power of understanding molecular orbitals and how they describe how new carbon-carbon bonds are formed. So, back to the Diels-Alder. Now that we know the Diels-Alder, which is a 4 plus 2 cycloaddition, let's look at some examples so we can get really comfortable with drawing the reaction products of a Diels-Alder, which is symmetry allowed in the ground state. So the first thing you're going to want to do is take your diene, and you need to recognize dienes first off. I can see that's a diene, and now what I'm going to do is I'm going to redraw this so that it is in what's called the S-cis conformation. And note that I am keeping the stereochemistry of my double bond constant. Okay, so it's a trans alkene there. It's got to be a trans alkene here. All right, well, once I've drawn my diene in the S-cis configuration or conformation, then I can draw my dienophile right next to it. Oops, not that. And once I've done that, then I'm all lined up to draw my electron movement arrows. And that allows me to immediately draw my cyclohexene. Okay, so here's my cyclohexene. These are the two new bonds I made. And got to put the rest of this stuff on here. There's my methyl group, and here is my product. So start by redrawing your diene, line it up with your dienophile, write your electron movement arrows, write your product. There it is. How about this one? So now we've already got the diene nicely drawn. Just draw our arrows here. And that ought to take us to This is our cyclohexene OSIMe3. And what do we have over here? Again, here's the two new bonds that are being made, plus the pi bond. And what do we have over here? Well, now we have an aromatic ring. So there's a reason why this guy is in brackets. Can you imagine a six-membered ring with an alkyne in it? I mean, that's got to be pretty highly strained, and it is. It's incredibly strained. This is called benzine, and we know of its existence because of reactions just like this. It can be trapped in a Diels-Alder to give the product shown. So that's the Diels-Alder. There are certainly other considerations to it, like when I line up my diene and my dienophile, I can line it up either the way I've shown it on the top with the carbonyl pointing up or the carbonyl pointing down. Remember what I say about alkenes. Whenever you're working with an unsymmetrical alkene, you have to think about regiochemistry. So this would lead to two completely different products. Which one will be the major product? That's the regiochemistry question. And when you look at something like this Diels-Alder, I'm generating a compound that has as many as 4 stereocenters. I need to wonder what we're going to have. Are we going to have RRRR, SSSS, RSRS? What am I going to have? So luckily, we'll save those for the next mini lecture. But in the meantime, well, how are you going to go on an extremely interesting and fascinating adventure in the outer space? You're going to plan it? Ugh, that was a pretty bad delivery. I think I probably should have made this slide about the exciting discovery of gravitational waves. Pretty amazing and cool stuff. But enough of that. Doesn't have carbon in it, so we're not going to pay any attention to it. And we'll see you Diels-Aldering in class.